Good morning, children. Today, let us discuss how to calculate the potential energy of an electric dipole when it is kept in an external electric field. We have already discussed how to calculate the potential energy of an electric dipole. Here, when an external electric field is present and an electric dipole is kept in that electric field, how to calculate, or what will happen to the electric dipole, how to calculate the potential energy of that electric dipole. And let us consider an electric dipole minus q and plus q separated by a distance 2a placed in an external electric field. So the direction of the electric field is here given in this direction. This is the direction of the electric field, external electric field. And here the direction of the dipole moment, electric dipole moment denoted by P, is always in the direction of electric field at the positive charge and opposite in the negative charge. Okay, here the direction of the electric dipole moment is opposite in direction. At positive charge it is in the same direction of the electric field. The negative charge it is opposite to the direction of electric field. So therefore, these two opposite charges, the magnitude is same. The magnitude is same, and also the direction of the electric dipole is opposite in at two ends of the electric dipole. So this electric dipole will always align to the direction of the external electric field, or the electric dipole always try to align in the direction of the electric field with a force or with a torque. Here the force, since the electric dipole moment is opposite in direction, here the force, the net force is 0 here. Okay, because in both end of the electric dipole it is opposite in direction. Even though the magnitude is same, they are opposite in direction, so the net force applied on the electric dipole is 0. So therefore, and this electric dipole will rotate in this clockwise direction. Okay, electric dipole is rotating in the clockwise direction and always try to align with the same direction of the external electric field. And now also this electric dipole is placed in the external electric field in such a way that it makes an angle theta with the direction of the external electric field. In order to move this electric dipole in the anti-clockwise direction, so we need to apply an external torque. Though the electric dipole moment is opposite in direction, and also the net force exerted on the electric dipole is 0, but a torque is experienced on the electric dipole, which is always rotate the electric dipole in the clockwise direction. And in order to rotate this electric dipole in the opposite direction, that means the anti-clockwise direction, so we need to apply an external torque in the anti-clockwise direction, whose magnitude is almost equal to the torque experienced on the electric dipole. So the torque is experienced by the external electric field, whose value is same everywhere in this external field. So if an external torque is applied on the electric dipole, that neutralize this, whose magnitude is equal to the torque experienced on the electric dipole. So it moves the electric dipole in anti-clockwise direction without the acceleration. So it will move slowly in the anti-clockwise direction without the acceleration due to the external torque we applied on the electric dipole. The value of torque is experienced on the electric dipole. The torque is equal to the electric dipole moment into the electric field, and that is equal to, and also the electric dipole moment and the electric field, they are separated by an angle theta. So this can be written as P into E sin theta. And assume that if due to the external torque we applied on the electric dipole, it moves this electric dipole at an angle from theta to theta 1, or theta 1 to, suppose this is the angle theta 1, and it moves at theta to theta 1. Then what will be the work done here? It rotates the electric dipole in the anti-clockwise direction due to the external torque we applied. So there is a movement, there is a displacement, and this the electric dipole moves from angle theta to theta 1 to theta 2. Then there is a movement and a torque is, external torque is applied on the electric dipole. Then there will be a work done. Then what will be the work done? That work done can be written as dW. dW is equal to the torque applied and the angle moved, that is the d theta. T torque external into d theta. And in order to find out the total work done, so we need to integrate this quantity so that we will get the total work done W, that is equal to integral of, from where theta 1 to theta 2 we apply the limits, theta 1 to theta 2, gain torque external into theta into d theta. The value of tau external we already know, tau is equal to P into E into sin theta. So we substitute the value here, integral of theta 1 into theta 2, that is P into E sin theta, and theta into d theta. Now on integrating here, the value of electric dipole moment and the value of this electric field is constant at this case. So everywhere the value of, even though it rotates in the anti-clockwise direction or clockwise direction, the magnitude of the electric dipole moment is everywhere is same. So it has a constant value in this external electric field, and also the electric field produced is also constant at every point inside the field. So therefore these two terms are constant terms. So these constant terms can be taken outside, that is equal to P into E. And now we integrate this sin theta. Okay, on integrating sin theta, what we will get? Minus cos theta, and we apply the limits from theta 1 to theta 2, and that is equal to the work done, W is equal to P into E cos theta 1 minus cos theta 2. Okay, the work done here is equal to P into cos theta 1 minus cos theta 2. It is from the initial to the final. Okay, that is the work done. Now here the work done here. Okay, what is the work done? What is the magnitude of the work done here is stored as potential energy of the system. So if the potential energy, if you write the change in potential energy delta U, okay, that means from the initial point to the final point. So what gives? That gives the change in potential energy at the angle theta 1. It has a potential energy, and when it moved to the angle theta 2, then the potential energy is changed, and that potential, the difference between these potential energies gives the change in potential energy. That is the U2 minus U1. That means the potential energy at the final angle minus and the potential energy in the initial angle. That is equal to P into E cos theta 1 minus cos theta 2. Okay, if you want to calculate the potential energy at a particular point of the electric dipole, then instead of this theta u, the change in potential energy will write as u2 minus u1, that is equal to P into E cos theta 1 minus cos theta 2. Here the value of u1 is equal to 0 when the value of theta 1 is equal to 90. So cos 90 is equal to 0 then, minus P E into cos theta 2. In general, potential energy of an electric dipole with an inclination theta from the direction of the electric field is given by, that means that finally we can conclude the equation potential energy U at an angle theta is equal to minus P into E cos theta. And if you get, when we represent this in the vector form, we can write P into, and this is the equation for the potential energy of an electric dipole in an external electric field.